Okay, so this video is all about how to calculate delta H from bond energies. So back in Unit 7, I'm just going to talk to you. Back in Unit 7, we learned about delta H, enthalpy, and there was a fifth type that was calculating enthalpy from bond energies that I said we would learn about in Unit 10. Well, that's what this is. This is very straightforward. So when we bond energy, in order to break a bond, you have to put energy in. Typically, when bonds form, they release energy when they form. So in order to break them, you have to put energy in. So overall, energy has to be added in order to break bonds. So it is endothermic. When you form bonds, it's released, it's exothermic. So in order to find delta H, which would be for the whole reaction, what you're going to do is going to be the sum of the delta H's for the bonds broken minus the sum of the delta H's for the bonds formed. Now, the bonds broken are the bonds of the reactants, and the bonds formed are the bonds for the product. So this one is backwards from every other delta H calculation you've done. Normally, delta H is the sum of the enthalpy of formations for the products minus the sum of the enthalpy of formations for the reactants, but this one's reversed, okay? So just be aware. That's another reason why I do this with bonding versus with regular Unit 7, because this is the one formula that's backwards. And so to help alleviate confusion, we just do it separately. So we're going to call this revised Big Mama. Okay. All right. So let's do some practice. So we have this one, and in my next video, I will be reviewing how to draw Lewis structures. So for this video, I'm just going to give you what the Lewis structures are, and next one, I will talk about how to draw Lewis structures. So we have this reaction. We're not going to worry about the names. Those are two organic compounds. Let me draw out what's actually happening here. So I'm just going to draw it over here. We have carbon that's bonded to 3 hydrogens that is bonded to a nitrogen, and then that nitrogen is triple bonded to a carbon. And it doesn't matter for the problem, but there is a lone pair on that carbon. And then that is going through a transformation to this. Do you notice how in this we no longer have a carbon-nitrogen single bond, but we have a carbon-carbon single bond? So let's look at, so this is my reactant, and this is my product. On my reactant, we have 3 carbon-hydrogen bonds. 3 carbon-hydrogen bonds, and that bond energy is 413. We also have 1 carbon-nitrogen single bond, which is 305, and then a nitrogen-carbon triple bond, which is 891. So we're going to add all of those up. And then we're going to subtract the bonds that are being formed. We have 3 carbon-hydrogen bonds. We have 1 carbon-carbon single bond, and 1 carbon-nitrogen triple bond. So we'd add those up. But we can cut out a few things here. For example, the 413, or the 3 carbon-hydrogen bonds, they didn't really break and reform, so we can actually cancel that out. Same thing with the carbon-nitrogen triple bond. Net, it didn't change. So really, it's just going to be 305 minus 347. So our delta H is 305 minus 347, which is negative 42 kilojoules per mole, which is our delta H. Okay. So an overall decrease in energy, so it's going to a more happy state. If we actually calculate delta H using Big Mama from Unit 7, we would have gotten the same answer if I used all the delta H of formations. All right, another one. Actually, this is a chart of all of the bond energies that we will be using. There's one portion of this that I want to point out, and that is right here. The carbon-oxygen double bond has a little asterisk. All right? That, the 745, is the bond energy for the carbon-oxygen double bond in anything but CO2. Okay? In CO2, which we have 2 carbon-oxygen double bonds, that bond energy is 799. It's just a weird exception, and that's because of the shape of the molecule and stuff like that. It makes that bond energy a little bit higher. All right, so just keep that in mind. There's that asterisk. All right, so looking at this one. So this one already has the Lewis structures drawn for us. Please be aware that coefficients will change the number of bonds you have, okay? So let's just go left to right, just left to right. So in this is methane. We have 4 carbon-hydrogen bonds. And if I look on the chart on the previous page, that bond energy is 413. And then we have, in O2, there's 1 oxygen-oxygen double bond, but we have 2 molecules. So there's 2 OO bonds that are double. That's 495. Minus, in CO2, we have 2 carbon-oxygen double bonds. And remember, that one's the weird one. It's 799. Plus, in water, we have 2 oxygen-hydrogen bonds, and then there's 2 of them. So we have 4 total at a bond energy of 467. So when I do all that math, you should get negative 824 kilojoules per mole. And that is the delta H for this reaction based off of the bond energies. Okay. 2 more practice problems and then this video will be done. This one, like I said before, I'll go ahead and draw those Lewis structures for you. Next video, I will review how to draw Lewis structures. But we have, we have nitrogen, N2. Nitrogen is 2 nitrogens triple bonded to each other, and each one gets a lone pair. The lone pairs aren't going to affect the bond energy, but I just cannot draw an incomplete Lewis structure. That's my own personal thing. And then we have 3 hydrogen molecules, which each hydrogen is just H single bonded to H. And then that's going to 2 ammonias. Ammonia looks like this. Okay. So on the, I'll do green. On the reactants, we have a nitrogen triple bond being broken. And we have 3 hydrogen-hydrogen single bonds, and that's 432. And then on the product side, we have 6 nitrogen-hydrogen triple bonds, single bonds, because there's 3 in ammonia, and then we have 2 ammonias total. So that's 391. So the delta H should be negative 109 kilojoules per mole here. This is very straightforward. Should not be real difficult. Those of you that are sitting in the classroom right now are probably learning this just by watching a little bit while you're doing your POGIL. All right, and then the last one, I'm just looking up values on the chart, which again are on page 6. This chart here. So, this molecule is called ethane. We have 2 of them, and there is 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds in ethane, and then there's 2 total. So that's 12 carbon-hydrogen bonds at a bond energy of 413. In that molecule, we also have a carbon-carbon single bond, and then there's 2 of them, so 2 times 347, plus 7 oxygen-oxygen double bonds, which is 495, minus, on the product side, we have 4 CO2s and 6 H2Os. Our 4 CO2s, each CO2 has 2 bonds, 2 oxygen-carbon double bonds, so 8 total. 8 times 799. I'm just pulling all these numbers from the chart. Plus, in water, there's 2 oxygen-hydrogen bonds, and there's 6 water molecules, so 12 times 467. And that should be negative 2881 kilojoules per mole. And that's how you calculate bond energy. It's literally just from the Lewis structure of all the molecules in the reaction and using the average bond energies from table 8.4. Next video will be on reviewing how to do Lewis structures, so stay tuned.